Okay, Claudio, Ismael, good to have you here. This is the 23rd lecture of Physics 140 this semester, and we're getting closer to the end. I think in terms of subjects, we need to see a bit of semiconductors and a bit of nuclear physics, and I think that would be the end of the semester. So we still have a few lectures to go. So let me review a bit what we were doing before. We were looking at diatomic molecules, and those things could be want to mechanically model as a spring and a rotating mass, and a rotating mass has this thing that the angular momentum of the system could be expressed as the kinetic energy of the rotating body as L squared divided by 2I, where L squared now is h bar squared times L times L plus 1. And so we get essentially a spectra that looks like, not even a spectrum. We get a set of energy states like this. Here in blue, I have the vibrational energy levels that are linked to the vibrational part of the Hamiltonian. That is actually give values of h bar omega, where omega is somehow linked to the spring constant, the associated spring constant of a molecule. There's not really a spring in between the atoms here. What really it is, it's some sort of a attractive potential that has a minimum, and you can always expand a potential around a minimum as a function of and write it as 1kx squared, something like that, and k then will be the equivalent of the potential that a spring could have. So that's why we recognize, even though the origin of the interaction between these two atoms is through electromagnetic interactions, you can always model that as a spring constant, you know, just by taking the second derivative of the potential and find out what it is. Okay, and at the end, when you mix the two things, you find that you since, and this is something you have to actually verify, that the vibrational modes are very widely separated, the blue lines, okay? Because it has to do with the characteristic values of these two things, the reduced mass for one side and the spring constant, and the other one is simply the vibrational modes that are, you know, depicted here in orange, and for each vibrational level there is a rotational spectra too. So here is n equal 1, L equal 2. So L means that the molecule is somehow, if it is n equals 1, you can think that the spring is actually, you know, in the wide side of the thing. It has one excitation of the vibration, and it's also rotating with angular momentum larger than 1. And when you mix the two things and put in the numbers, it turns out that the spectra looks like this, meaning you have this wide separation between energy levels related to vibrations, and you have a smaller separation linked to rotations. Okay, and what you can only see here are actually optical transitions, meaning the emission of a photon between two of these levels, if this actual selection rule is fulfilled, meaning the difference between the two rotational levels could be plus or minus 1. So that is a restriction, because the photon actually has an intrinsic angular momentum, L equals to 1. It's a special angular momentum because the mass of the proton is 0, but it does have angular momentum. It has to do with the rotation of the polarization of the photon. Okay, so you have two possible outcomes of this thing, two possible outcomes. And for example, this guy here from L equals 2 to L equals 3 is an allowed transition because delta L is equal -1. And this one from L equals 3 to L equals 1 will be a delta L -2, which is not possible. So this transition in red here is not allowed. So when you have a spectra, you have to really be careful to understand which are the allowed transitions depending on this selection rule that we have here. Okay, so this is sort of what we saw at the end of last lecture. So I wanted to take it over, and you know, molecules and the basic thing is actually binds together few atoms. And the simplest thing is diatomic molecule, what we were just saying. And the other extreme of things is when you form a solid, meaning many atoms coming together. Okay. So what it says here, my apologies, this thing is actually cut down. I actually stole this view graph from this website, but I'm sure in the there it is. Okay, so I'm giving proper credit to this. I like because the images are very nice actually. So a few things that are very important here, that except for helium, all substances form a solid at sufficiently low temperatures. Okay, even mercury can be solid if the temperature is low enough. Okay, so it means that they form an ordered structure with the atoms in the solid, you know, having a regular array in three-dimensional space. Okay, essentially you can think of the solid as built of a superposition of what we call a repeating cell, we call a unit cell. And we repeat this cell in many places, and that's a solid. What binds the solid together? Well, it really depends. You can have both meaning any of the ways we actually study that the atoms bind together. This is exactly what happens in a solid. You can have covalently bonded solid, you can have ionic solids, you can have van der Waals solids. You know, van der Waals solids is usually for molecules, for molecular solids, meaning you form a molecule by covalent bonding, and then the interaction between the molecules is van der Waals, and that can, you know, make up an additional solid. And it's a covalently bonded solid. So in general, these are the structures of the material, and you know the actual how do we know this about this? We actually have a tool which we know about something about it, which is X-ray crystallography. We use the X-rays and the diffraction of X-rays, similar to the diffraction of electrons that we saw in a few lectures back. We use them to understand the details of the distances and whatnot inside a solid, and so that this is how the picture of how the atoms are arranged in a particular solid comes from. The distances are very small, the order of a few angstroms. So we have, you know, this is only is the right tool for actually doing that, you know. And here there's another statement here that many inorganic compounds may be initially described in terms of simply packing of spheres. What you could think is that each of the atoms is, the atom is not the nuclei, okay? The atom is the nuclei plus the electrons, and the electrons, they have some sort of kind of a spherical thing on average, that could be described as the size of the atom or the radius of the atoms, and we can actually measure atomic radius depending on essentially the crystalline structure that they form. Okay, so this is the thing. This is what we think it's could be a possible array of atoms. We have a plane here of these spheres all in contact with each other. You know, going beyond the radius to a smaller thing will be a superposition of electrons here, and that will bring the energy of the whole thing up. So there's the right play that has to be, you know, fulfilled for this thing to be the lowest energy thing and actually bind. But we know they bind together. So that is a fact of reality. What we need to know is a way to describe them. This is a possible array of atoms. This will be sort of a square array, and here we have a triangular array in a closed pack thing. You can see that the actual white area in this diagram here is smaller than in here. So it means that the packing of the spheres is more efficient in this case than in this case. And that has to do many things with the electronic structure with the geometric structure of solids in general. In this particular case, you can see that I can, let's say I'm giving you the task of putting a set of 500 tennis balls inside a box, a carton box, and you have to put them in. How would you do that? What is the most efficient way? How you put the maximum number of balls inside that pack? And this can come as the solution. Okay, so many crystalline structures are related to this. Okay, so to the fact that you can get a closed pack structure, and in this particular case, you can see that if I put a second layer here, where do I put the second layer? I am putting the second layer where there is a white spot there. Okay, I put a second layer where there's a white spot. I put a second layer where there's so the red atoms, the red spheres here, are placed on the hollow sides of the first layer. Okay, and then I build this layer over here. But there's something interesting here, because in the hollow sides here, they have two options, because I have one hollow side on top of another atom of the top of the first layer atom, and I have a hollow side on top of an empty state here, of an empty site. So I have two options to actually put the second layer, and depending on that, depending on the stacking that I use, I can form different symmetries of a crystal, and that is really related to the stacking of these spheres. Okay, and somehow there's still the link of how do we think of atoms as spheres. I sort of crudely described it before, but that's about it. Okay. These are the common atomic structures that materials have. This is a primitive cubic. Okay, so this is not a very efficient one. Actually, there's only one element in the periodic table that actually has this structure, and it's polonium. Okay, and how does it happen? Well, you have a cube, and you have one atom in each vertex of the cube. So essentially, if you look at the cube here, this is an interesting question. How many atoms are there per each one of these cubes? You have to remember that when I form the complete solid, I have to repeat this infinitely, cubes all over the place. So this cube over here, this atom over here, is part of 8 cubes. You see that? This diagram actually helps to understand that, you see, because in this atom, the distance between, it is drawn like this to just show the symmetry, but actually the actual thing is sort of like this. The distance here has to do with the atomic radius of each one of the atoms in the corner. So this guy would be this guy over here, exactly that one. But 1/8 of the atom is that is in this corner belongs to this particular primitive unit cell. So this unit cell actually has one atom per unit cell. 1/8 for each corner of the cube. Okay. Then there is another geometry which is also fairly popular, which is this. This is it's a body-centered cubic, and as you may realize by now, you know, this structure has 2 atoms per unit cell, meaning that guy in the middle and the 1/8 of each of the corners, and produce this So this structure will have 2 atoms per unit cell. What would that mean? Let's say that this is a monovalent electron, monovalent material, the whatever material we have here. You know, it's, let's say, iron. Well, iron is not monovalent. It can have a valence of 2, 3, whatever. Okay, 2, 3, and 4. But let's say it has valence 2 for the matter of things. So it means that if I have 2 atoms per unit cell and this thing have valence 2, so it means that there will be 4 electrons lying around that I have to locate somewhere per each cube like of this size. Okay, so this is a characteristic thing of a body-centered cubic structure. The other one is this one is a face-centered cubic. This is also a closed packed structure. It's a square closed packed structure compared to the other one that was an hexagonal closed packed structure. So the cubic closed packed structure is called a face-centered cubic, and you can see, look at this face over here. You have 1 atom in each one of the corner plus 1 atom in the middle of the face. Okay, and if you want to count atoms here, this is a bit harder than before. You know, we are seeing all the atoms in this diagram here. So for each one of the faces, you have half an atom. So we have 3 faces. It's a cube. It's a, you know, dice, and so it has 3 faces, 6 faces. So you have 3 atoms coming from that, and plus 1 atom from the corner. So in total, you have 4 atoms per unit cell in this case. So this is sort of the calculation done here in the corner. And here are some sort of dimensions associated with this that you have to be, you know, careful to calculate if you actually need to calculate distances inside and whatnot. Okay. There are 14 structures, 14 structures that can actually fill the space, that are called Bravais lattices. Bravais lattices because Mr. Bravais was the first guy to actually propose them. And you know, these are the cubic ones that are on top here, the simple cubic, the body-centered cubic, the face-centered cubic. But then there's variations of that, the tetragonal one, the orthorhombic one, the hexagonal, the monoclinic, triclinic, and whatnot. Okay, and so this is something one should know, that there are no more than that. They're not 28. They are only 14. They are not, you know, and these are the structures that you can actually have a system display in a system. There's a trick part here that you can have this system, for example, with a base. Okay, this is a tricky part, and that you can have the unit cell look like that, but you can place an atom in a certain position inside here, which is something that doesn't change the cubic structure, but it could modify the arrangement of atoms, but they are all anyway based on these 14 unit cells. I'm going to come back to an example to explain you that. Okay, so these are this is the periodic table of elements, and here we can recognize, for example, that all these guys here, the alkali metals, are all BCC. Okay, so they correspond to this structure here. The cubic I is called. Okay, so they are all BCC. This guy beryllium here is HCP, which is hexagonal close packed that is the acronym for HCP, and correspond to whatever I showed you before in the first view graph, this guy. So it will be, this is hexagonal close pack. There is the hexagon, and there's the, and it really depends on what the actual sequence of layer, because it should be a material which is A, B, A, B. Let's say the other guy is also in here, and then this will be an A, B, and A, B, meaning the third layer would be equal to the first layer. But you can have materials that are A, B, C, meaning they are using the hollow sides in the third layer. Okay, so this is sort of what the reality is, and here you have all this distribution. Not only this guy here, copper, silver, and gold, which is something we are sort of, at least copper we should know. You know, we get most of our resources in the country through copper. So remember, copper is FCC, is cubic closed pack. Cubic closed pack means FCC. It's an FCC structure. It's the same as silver and gold. Okay, iron, which is another material, it's at low temperature. It's a BCC structure. Okay, and as I told you before, polonium is the only one that adopts the cubic structure, and the simple cubic structure in the whole periodic table. Okay, and then this is the thing of the sequences here. This is what difference this HCP, CCP. It really depends on the sequencing of the layers. If it is AB, 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 or AB, AC, or whatever, you can have many sorts of combinations. And depending on that, the thing is quite complicated here. And the actinides, which is the next row that should go here, it's a lot more complex than this. Okay, so the actual structure, or how the things actually pack together to form an extended solid, may differ a bit. The binding is the principle is the same thing as we have seen before, meaning it's covalent bonding, metallic bonding, ionic bonding, essentially for materials, and for molecules is van der Waals. Okay, but this is an example of what I was telling you before. This is the pressure in bars here, and here's the temperature, and at reasonably low pressures and you know, temperatures, low temperatures. This is Kelvin, so room temperature is here. So this will be the stable structure of iron under this condition. But if I change the temperature, raise the temperature, for example, at atmospheric pressure, I can go to an FCC structure for iron. And if I keep raising it, I make it a liquid, which makes sense. But this is a structure, and it can also go to HCP if you actually raise the temperature a bit. So iron is a pretty interesting material in terms of most of the properties of a material change if you actually modify the structure. You know, this phase is magnetic, this phase maybe not. Okay, so the electronic structure is actually changed, which we know because the electron play a role in how the actual atoms are bound together. So this is an interesting aspect that should be taken into consideration. This is something we know. This is our everyday salt, okay, and it has this rock salt structure, which is two mixed FCC structure. If you look at the red guys here, which are the sodium, look, there's a red guy there. So that forms an FCC structure. And this also forms an FCC structure. Look here, there's nothing in between here. There's no sodium in between here. So sodium by itself form an FCC structure, okay? And the chlorine atoms does the same thing in in the missing was displaced by half a unit cell. Okay, so this combination of structures here is what is called a rock-salt structure, and many materials, as being explained here, form something like that, but they have the basic structure of what I was telling you before. Okay, this is ionic solid. It means that the binding, as we already learned from the example that we studied in detail, is forming an ionic bond. Okay, so it's that's a model. This is another ionic solid and another option for the structure of the ionic solid. This is not a body-centered cubic structure. Okay, this is a cubic structure with a base. A body-centered cubic structure will mean that you will have a cesium atom here. I'm sorry, a chlorine atom here in the middle. That is not a structure that exists. But well, cesium, on the other hand, if all these atoms are cesiums, or if all the balls in this diagram are red, that is exactly the structure that cesium has. Cesium has a body-centered cubic structure. Okay, but it means that when I describe it as such, it means that all the atoms are the same material. Okay, the same element. Here, this is not. This is a cubic structure with a base. There is a cesium atom halfway in the diagonal of a simple cubic material. It could be a matter of language, but you don't say this is a BCC structure. Okay, and there are many ionic solids that have the same structure. This, on the other hand, is a zinc blende structure, which is formed by combining zinc and sulfur. And look again, the sulfur atoms here are the green, the yellow atoms in this thing. And what do they form? They form an FCC structure. You can see here, this is a face-centered cubic here. This is also a face-centered cubic. This also facing, this is a face, one in each corner and one in the middle. But apart from that, from each sulfur atom displaced by a quarter of the diagonal in this direction, there is a zinc atom. For this guy, is there. For this guy, displaced is there. The displacement for this guy is there. The displacement for this guy, I'm sorry, the displacement for this guy is here. The displacement for this guy would be something that is outside. But each sulfur atom has a zinc atom displaced a quarter and a quarter and a quarter. Okay, and how does this feel? Look what it is. This if you look at the, let me see, do I have the FCC structure somewhere? No, this is the FCC. If you look at the FCC structure, it has a lot of room inside. Okay, that could be used to put atoms, and then the configuration that I'm actually showing you, this guy has an atom in this side here. You can divide this cube in eight cubes, 4 on the top and 4 on the bottom, which are, I'm going to draw here with the laser pointer. Here goes to that extreme, comes to the middle, and goes up to this middle here, and that's the face of this small cube. In this small cube, there is no zinc atom in the other configuration, but in the front one here there is one, because there is this guy and it has a zinc atom there. This guy has a zinc atom here. So from these 4 cubes in the front side, you will have 1 atom here and 1 atom there. And in the back, you will have 1 atom there and atom there. They will be crossed, okay? I hope that my description was not that bad, that you could actually see it here, see? This guy and these guys are in the front half of this cube, and these other 2 guys are in the back. And if these are in this diagonal, the other ones are in the other diagonal, okay? So you are feeling very much completely the 4 spots where you can put atoms inside this thing. This is called a zinc blende structure. In the case of a zinc blende structure, if all the atoms are the same, this is a structure that diamond has. This is a structure of diamond. This is a situation now. Since these are carbon atoms, they paint them black to make you feel the picture. But these atoms here are in the same positions as these guys, and this is and now we call it the diamond. And this diamond structure is the same in silicon and germanium, and this is called zinc blende structure because these guys and these guys are different, the same as before. But the zinc blende structure, when the position where the zinc atoms are is replaced by the same element as in the case of sulfur here, this will be a diamond essentially. This is a diamond structure. Okay, and if you look at the diamond, they are formed out of pyramids. So they have these tetrahedral things that have this triangular face. And here's the one. This is in this face, and this is in that face, and you can draw a line there, draw a line there, draw a line there, and you can see this is a face of the pyramid. And you can find that the other face, this face over here, this guy here that goes to there, it has the same size of this triangle that I have just drawn. Okay, so, and this atom here is in the middle of the tetrahedron. Okay, it's in the middle of it, meaning it has this triangular faces. It has 4 faces. That's what tetra means, and there's this atom that's in between. Okay, all the atoms in the solid in this particular solid have the same structure. You can always draw for each atoms in this model. You can always draw a tetrahedron like that. Maybe some of the tetrahedron for these guys is outside. Okay, but all of them will be inside of a pyramid like this. Okay, and so this is a very striking thing that has to do with the properties of a solid, of diamond in particular. Okay, with the vibrational properties indeed. This is a solid that is covalently bonded. We saw before what the covalent bond was. This is very directional bonds here, and these bonds are all the same. They have the same angles. They are simply rotated to one another. Okay, so this is something typical of a covalent bond, which is a very directional bond, which is in contrast with what we studied before, which is the metallic bonding. Metallic bonding is something is the energy of embedding an ion in a sea of electrons. And this thing is actually it's not very directional. This is why you can bend the metal, okay, and still hold the structure of it, which is different from a diamond. If you bend the diamond, you break the diamond. There's no, because the bond is really covalent and directional, and in this case, you somehow this thing could be in any direction, and you can somehow twist it and induce a defect in the microscopic structure, but the integrity of the material will still hold. Okay, so this feature here is something very relevant for most of the metals. So meaning you put inside you don't put, the metal comes like that. In a system like a metal, you can actually, this is sort of what I told you before, is a generalization of the covalent bonds in materials, and you can get that by having delocalized electrons linked to the atom, that instead of being directional, they could be anywhere. Okay, and so there's a way to actually model these electrons. You can actually somehow describe them, and this is the 0th order model to describe the electrons in a metal, is that you can say, look, these guys are bound to a box. The electrons are bound to a box, and they could, move inside the box freely. They cannot go out of the box. Okay. So if you want to describe the conduction of electrons on a metal, that is the first order approximation, meaning you can say, well, it will be no interaction between other electrons and no interaction with ions. It means I have a box and I put a bunch of electrons inside, and look, what do they do? And under what conditions? That is similar to what happens in materials. And most of the situations, it is really a good description of the conduction of electrons in materials. And that's why we are going to try to study this model in detail and what comes again. So this is what I was telling you before. This is what we plan to describe. We are going to describe what is called the free electron model. In the free electron model, we are saying the electrons are bound in an infinite potential well in 3D. The volume of this thing is equal to L cubed. So the distance in this direction is L, in L and L, okay? And L here is some sort of macroscopic value, meaning it's not comparable to the distance between the atom, but it's several unit cells in this direction, 1,000 or millions, okay? So it is really depends on the size of your solid or your macroscopic solid, okay? So how are we going to describe this model? First we're going to neglect interaction with ions. So the electrons are not going to interact with the ions. The electrons are not going to interact with other electrons, okay? And we're going to see how far this simplification gets us. So the electrons are confined to a box of side L. We did this already, isn't it? Yeah. We studied the thing. Now we're going to put many electrons inside this box. So this is going to be field not 1, 2, or 20, as I did in the homework last time, but it's going to be, thousands or millions or 10 to whatever, big number, Nonetheless, the energy of the confined states is given by this number. So not every energy is possible for electrons confined in a system like this. How do the energy increase? Is something like that. It has the L square at the bottom here. It has this constant. This is the mass of the electron. And this here, this number is an x square and y square and z square. These n square are integer numbers square. Okay, that's what we know. Okay. Since the numbers are big, I'm allowed to do this approximation that I'm doing here. So if I'm drawing this n space now, and each time I have an x, an a y, and an z, I have a state. I'm interested in counting the states available for each electron, for the electrons in the system. Okay. If I have the electron, I want to know where they are. See, the picture is the following. Let's say I have something as a material like this. Let's assume that each of these guys are going to contribute with 1 electron to the sea of electrons in this system. And I have how many of this guy? Well, it will depend on the size of this volume here. But I have a density of electrons being contributed to this thing. And the question is, if I use this free electron model, what would be the highest energy that I could feel? The same problem that I gave you before, but now what I want to find out is when the number of electrons in the box are huge, how high does the energy go? We know that if we reduce the size of the box, if this goes very small, the energy will go up, given this expression. And if this is a macroscopic big size, the energy will go down, okay? And but there's a limit. The limit is there's something that has to do with the density of electrons that I have inside. It's when I change the size, of this thing, I actually increase the numbers of electrons also, because the density of the material that I will have inside does not change. It is not arbitrary for me to actually change the microscopic distance between atoms inside the material. So if I make a material bigger, I am including more electrons in the systems, okay? So this is the interplay that I want to understand. I want to see how do I feel the energies of this material in order to see how high is the highest energy that I could have. So this is something very striking of the quantum mechanics. This is a natural quantum mechanic effect, meaning if I had a solid that didn't have fermions as electrons, everything will be in the bottom state, meaning, and the properties of the material will be right different in the case of a solid if I have fermions or not fermions or not identical particles in the system, okay? So these are my energy states, and each point, n, x, n, y, and z, I forgot to draw the n, c point here, means one state, okay? So the thing is, the volume of each one of these states in this nx and y and c of each one of the state is 1, okay? Because it is discrete. These are discrete number of states. This is not a continuum, but now I'm going to calculate the volume inside this octant here, okay? The volume inside this octant here will be equal to the number of states below a certain energy value, okay? Do you just guys follow that? I hope that you do. Meaning, how many states do I have until this guy arrived to, and why I am using a sphere? I'm using a sphere because, look, the nx squared plus ny squared plus nc squared is equal to n squared, which is the length of the vector between the origin and the surface of the sphere that I have here. And so all the guys that are leaving, all the points in x and y and z that lives on this sphere, only on the surface of the sphere have the same energy. So I want to know exactly those are the ones. If I reduce the radius of the sphere, I will have another sphere that goes inside that has, you know, a different number of energy available for this. What I'm actually trying to calculate is the degeneracy of each of these states. And as you can see, if this thing is actually reduced to 1, the radius is reduced to 1, the possibilities of what are the energy states that I could actually reach is very small. So the degeneracy is really a function of how long this NR is. I'm interested in counting state. Why I'm interested in counting state? Because I know that at 0 temperature, if I want to find the lowest energy configuration, I can put 1 electron per each state. Well, not 1 electron. Per each state, nx, ny, and z, I can put 2 electrons because I can put one with spin up and the other one with spin down, okay? So this is what I'm going to try to calculate in the next few graphs, okay? So this is what I told you before. These are the number of valid nx and y states, and then the total number of states that are contained in the octant of that sphere can be approximated by the closest integral value of, you know, if I approximate to the closest integral value, because it may not be an integral when I calculate it, that will be the number of states that has an energy less than the highest energy that's given by an R, which an R meaning is the radius, this radial direction, okay? So the volume of the sphere is this one, but it's not the whole sphere because n can only go from 1, 2, 3, whatever, going up, okay? So it doesn't have negative values, so I only have to count the 1/8 of the on this space. So that's why it is 1/8 of the volume of the sphere. So these are the numbers of states. The volume is equal to the numbers of states. So the energy, the energy of the state at the surface of the sphere is exactly equal to that. Is E is equal to nr squared times this factor. So what I'm going to do next is this is providing me a link between the energy of the outermost state with the value of nr, and this thing is actually telling me what is the number of states up to nr. The number of states available up to nr is given by that. Okay, so I want to use the expression that I could get from nr, from this thing, plug it in here, and actually write down an expression for the number of this number n, the number of states up to nr, as a function of the energy. As the energy grows up, as nr grows, the energy grows up. Okay, so I'm getting higher number of states if I go up. And well, it is very easy to, well, there's one correction here. I actually, this value here, if you actually do the math here, is 1/6 pnr squared. But here I only have 1/3. Why is that? Because for each nx, ny, and z, I can put 2 electrons. Okay, because, you know, spin plus a half and spin minus a half, and that will be the way of filling this thing without violating the exclusion principle. I cannot put another electron because there's no another quantum number to make a difference between the state, because otherwise the wave function will be 0 for that system. Okay, so if I do that, I could write the total number of states as a function of the energy to the 3/2. These are the total number of states inside this octant sphere. Okay, but now I'm interested in finding out what are the number of what I'm interested in finding out is what is the number of states for a particular energy. Meaning, what I'm interested in is the degeneracy, or what I call the G function. The G function is the density of states. So for a particular energy, what would be the density of state? How do I calculate beginning from this? Simply I said dn and take the derivative of this and write the differential. So I assume this things is a continuous variable, and I take the derivative of this expression and I say dn, the number, the incrementing number. You can now draw some sort of a very small number when you change the nr only by a fraction, and you can draw some small differential volume there. And in that differential volume, you want to find out how many states are there in that differential volume that are associated to a single energy. Okay, this is what we are doing there. So the number in that differential volume, I didn't draw the differential volume, I should have drawn it, okay, is equal to this expressions times dE. So if the energy, so this really has to do with the energy E. The energy E is linked to the radius with respect to the origin, meaning this radius with respect to the origin is directly proportional to the energy. Okay. Well, the radius square. This nr square is proportional to E. Okay. So this is what we use to actually arrive to this expression here. And now we have the total number, not the total, the differential number in this small volume is equal to GdE times dE. Okay. And GDE has this expression that is here. I have a homework here. What would be GDE for a free electron gas confined in 2 dimensions? What should be different in 2 dimensions? Well, you go back here. First of all, you don't have a sphere in 2 dimensions. You have an X and a Y. So essentially, you will have a circle. The third axis doesn't not exist. Okay. So this is, I want you guys to calculate this expression GDE for a 2D system. So instead of 3D as it is here, for a 2D system, what would that be? This something with this homework is somehow related to the new materials. For example, graphene. You can define a free electron model for graphene, for example. Okay, and what you would like to do is find out exactly how to define that. And this here is the energy density, meaning this is the number of states per energy per volume. Okay, no, the volume is here. This is the density of states. This is the number of states per unit energy. You have to multiply by energy and you get the total number of states in the system. Okay, let's look at that. Now, I want to calculate the total number of electrons. To calculate the total number of electrons, I have to multiply the density of states by the probability that a number that one of these states is occupied. Okay, and because I want to actually do this as a function of temperature. If temperature is 0, we know what the solution is. All the lowest energy state will be occupied. That's it. Now, if I raise the temperature a bit, it means that some of the states above the highest occupied level will be occupied now. Okay, so you will have the distributions of electrons changing a bit. How would that change? How is that changed? This is the solution to the question, and let me try to motivate it here, because I'm not going to be able to go through all the math to actually get to this expression. But let's say in the Maxwell-Boltzmann distribution, the number of particles in one energy state of a system at a temperature T is proportional to e to the minus e over kBT. This is the way it's done in an ideal gas. Okay, so the energy, if the whole system is a certain temperature, let's think, we can actually think of this as an electron gas. Okay, because if you have an electron particle, they are flying around and they don't interact with each other. Okay, but the main difference with the classical gas is that the distribution, the probability of this guys having a certain energy is e to the minus the energy of the state divided by kT. Okay, it means if the temperature, whatever the temperature is, the highest the energy state is, the lower the probability of that being occupied. Okay, if you raise the temperature, a certain state will have a higher probability of being occupied, meaning that's the meaning of raising the temperature of the system. You occupy higher energy states when you raise the temperature of the system. Okay. But when we talk about electrons, we know that electrons, that each state can only hold one electron, cannot hold more than one electron. Okay, so this is the main difference with this system here, and there is a little bit of a change on the way the probability is described, and the probability is described by this distribution here. F of E is the probability that one state with energy E is occupied at temperature T, and it's given by this expression here. And let me explain what it is. This is the energy, the same as this energy here. This is a constant value, which is the Fermi energy, which is, it's meaning, at least at zero temperature, is the highest occupied energy level. This is what I wanted you guys to calculate, or we wanted to understand. What was the maximum value of the energy that a system could have at low temperature, okay, of the electrons at low temperature. This is the Boltzmann factor, and this is the whole expression. This is called the Fermi-Dirac distribution function. And some of the properties of these functions are shown here. When this is the one when E sub when kT is equal to 1/40th E sub f. Okay, this is a small temperature. It's 1/40th the Fermi level. When the temperature is higher, the thing is actually start looking like that. See, they all go through the value of a half at the Fermi level. This actual expression goes to that value. When the temperature is very high, you know, this thing starts to distance itself from 1. At t equal exactly 0, this thing is actually a square. Goes here, it's a jump function, meaning it's 1 up to EF and it's 0 afterwards. Okay, so those are the extreme values that this thing could have, and this is the way it changes. This cannot go all the way to large numbers here. Okay, and even if the temperature is very low, when the temperature is low, you can occupy all the states evenly below this value of energy. If you wouldn't do that, you know, this is, again, this is the Fermi distribution for this particular value here. And remembering that only one particle, one fermion, can occupy each state, this is the distribution that works out, because it provides even number of states here to even the same probability to occupy any states below a certain value. But if you do the Maxwell-Boltzmann distribution at t equals 0, meaning 0 temperature, this is also 0 temperature. This is the Fermi-Dirac distribution for 0 temperature. This is the Fermi-Dirac. This is the Max-Boltzmann distribution for 0 temperature. You get only the occupation of the states with E equal to 0. It means you only occupy all your electrons will be in the ground state. This, we know, will violate the exclusion principle. We cannot have that. So this is why we have the Fermi-Dirac distribution that with t equals 0 provide the same thing for 0 from the state right at the side, and until what? Until you have all the electrons available in the system occupying an energy level with equal probability. Okay, and this is the distribution that you can have. Here, you know, you will get rid of all the particles. You can only have one particle in this state. Okay, and if you have a high, you arrive to a contradiction here, because you have many particles available in the system, and you only have location for one of them. Just forget it. You guys cannot be here because, you know, there's a contradiction. Okay, and the contradiction is solved by an energy distribution like this, where you can have, for all the possible states below a certain energy value, you can have a possibility of single occupancy of all the states, okay, with equal probability. Okay, when you raise the temperature, well, you know, you can sort of empty a bit some states and occupy some state above this value. Okay, so the number of electrons in a certain energy state, number of electrons now, because what we had before, GDE was the number of states. That is something we can calculate geometrically, because we count the states for each energy. This is what we did here. We count, no, this is what we did here. We count the states available for each energy. You did this in the example for the homework, okay? You go there, this state has these possible values, and it's a bit different here because now we're talking about big numbers, and we are approximating the discrete thing by a continuous variable, which is legitimate because we have a large number of electrons, okay? So, but now the number of electrons in a particular state will be the energy density times the probability of having that state occupied. And now what do I have to do? I have to add up all the states. I have to add up this expression for all the state to get the total number of electrons in the system. So the total number of electrons in the system, let's calculate this integral just in the case of t equal to 0. T equal to 0, we have the distribution function f of e goes like this, okay? So at 0 temperature, remember that this 0 temperature is not 0 Celsius, this is 0 Kelvin, okay? This is something you don't have to forget, that in all this expression, when temperature appears, something like that, this is always in Kelvin, okay? So the thing now is I want to calculate the total number of particles in the system, but the total number of particles in the system I know. Why? Because it's simply the number of electrons that they are available. So it, depending on what is the number of electrons available, it will be the levels that I have to fill up, which also makes sense. That I have a distribution of levels, I have a degeneracy of each one of the levels, and so in the first one I could put 1, in the second one I could put 2, in the third one I could put 4, and as soon as I start to separate from the origin, I could put more electrons. So if I know the density of the system, and I know the volume of the system, I know the total number of electrons that I want to locate there, and then I will know how high will they go, okay? And this is something, the highest energy level is something that depends on the material. Why is that? Because the density of electrons, the number of electrons per unit volume depends on the material that I am considering. Copper has, so many electrons available for every cubic unit cell, okay? Which is different from, let's say, iron, which is different from other materials, because it really depends on what the structure of the material is, meaning the geometrical structure of the unit cell, and the number of electrons that each unit cell has, okay? So the height, the value of the energy level is really material dependent, okay, in that sense, because it really depends on the density of electrons available, and the density of electrons available depends on the density of atoms and the valence of each one of the electrons. Okay. 4 minutes. Here we go. So the energy level is then determined by the temperature of the system. Okay, but at t equals 0, this is very simple to calculate, because now I replace f of e by the value 1 until when? Until the Fermi level, until EF, because after that it goes to 0. Otherwise, I will have to do this integral with the tail. I will have to integrate this thing, which is no big deal, but I don't want to get into that detail here. So, oops. So this is the value that it produced. So since f of e is equal to that, this is what I get. I get, this is I have already replaced this function in here. If I do that, well, I only have to integrate this expression here of g of e. And so the number of electrons in a particular energy system n of p is equal to this. You get the mass of the electron to the 3/2. You have the volume here. Where does the volume appear? We didn't have the volume at the beginning. Well, yes, we did, because the volume is equal to L cubed. It's this times that. Okay, so it's I should have written it somewhere. Here. with L cubed equals to V. So we have the volume now is a relatively important number. And look what I can do now. I can divide the total number of particles in the system by V. What do I have here? The number of electrons divided by the total volume is the density of electrons. And the density of electrons, as I told you before, is material dependent. Copper has a different density of conduction electrons than iron. Why is that? Because it has a different number of electrons per each cubic cell, because the number of atoms available for each cubic cell is different, and the number of valence electrons that are actually contributed to the sea of electron is different depending on the balance of the electron. If the balance is 1, only 1 electron will be contributed to the sea of electrons, which is the case of copper, silver, gold, and all the alkali metals. In the case of iron, it will be 2. Okay, so it really depends on which atom you're considering and which balance of the materials you're considering. And this is why, because this density here is controlled by the material. You defining this value, all the other things here is just constant value, the mass of the electron and the Planck's constant. So you actually can define the energy level, the Fermi level of the material just by knowing the density of electrons in the material. That's it. Okay. So this is the expression. Then the only thing you have to do now to understand what is the highest energy level occupied by the free electrons in a system with respect to the bottom of the band will be proportional to the density of electrons to the 2/3. Okay. This is a quantum mechanical expression. Quantum mechanics is intrinsically plugged in here. In which ways? The first way is the way we calculated the confined state in a box. And the second one, this is a direct application of the exclusion principle. Okay, so this is a complex quantum mechanical expression that you are actually learning right now. And now I'm verify the value of, I always, you have to know about copper. Most of our resources come from copper. So let's find out, where is the Fermi level for copper? We should know something like that. We are physicists, or you're engineers, you should know that, should know about copper a bit. And these are the information. I'm providing you with the information that copper is monovalent, only 1 electron. Okay, it has this structure, and you can, with that structure and this diagram here, you can actually, this diagram here, you can actually realize how many electrons per each one of these cube. And I gave you the size of the cube. So now you know how many electrons are there in the cube. You can calculate the density of the electrons in copper. Okay, this is something that you could do with this information here, and you can then estimate what is the value of the Fermi level. Okay, in copper. Well, all the rest is related, and here there's another trick question here. Is the equation of state of an ideal gas. This is a gas that is not a Fermi gas. This is classical gas. It's an ideal classical gas which has an energy of state that is like that. If you look at this thing, you have it in a volume. You have a certain number of moles of material. N is the number of moles in this case. R is a constant. So when the temperature goes to 0, in this equation state, the pressure will go to 0. The question is, does P also go to 0 for a Fermi gas? Well, the way I'm actually asking it here, it does not. So I'm asking you, can you calculate the pressure at 0 temperature for this gas? Okay, and the way to do this is the following: is you have this whole gas, And if you want to actually compress the whole gas, you actually have to make work. How much work do you have to do? You have to displace one of the sides of the cube by a delta X. What will that happen? That will raise all the energy levels a bit. So the change in energy here it's going to be equal to the work you're doing from the outside. And the work you're doing from the outside is going to be the force that you're doing times the delta X. And when you change that by delta X, see that when you change that by delta X, what are you doing? You're changing the L. The delta X is the L. You're changing the length. When you're changing the length, you change the energy levels. Okay, if you change the energy levels and you actually decrease the energy levels, you raise the energy of the whole system. So when you are actually making force on one of the walls, you're actually lifting the whole energy of the whole system. So you are making a positive work on it. If you are doing that, it means that there's a pressure against you. Okay, that pressure against you, you can calculate as the force you need to make divided by the area. The force you need to make divided by the area is the pressure. Okay, so you can actually that's a challenging problem anyway. It's even challenging for one of the professors in the class, you know. So this is an interesting. It's an interesting. You know, take a look at it. Ask me if you find something out. This is something we're going to look next. We're going to look next at the effect of binding atoms together. When we have atoms separated in space, isolated atoms have energy levels. This is an energy level. This is an energy level. This is an energy level. If we actually bring those atoms together to start forming a crystal, this is something mentally that we're doing, there will be a gain in energy. Remember when we studied the covalent bond in the model with the box? We went from something that has, you know, confinement of the electrons in each one of the small boxes where the electrons live in each atoms, and now when we bring them together, the electron can move in the whole two boxes, and that lowers the energy. That's exactly the phenomenon that happens here. So I have, you know, the isolated atoms, and now I don't have two. I have an infinite number of these guys coming together to form a crystal. So they lower the energy. So you actually start to, instead of having a single electron level for each one of the energy levels in an atom, in the case of a solid, and this is the actual separation, for example, equilibrium separation, some of the things of the states, the original state will have split into a region of possible values of energy that actually allows them to, two things they allow. You can put the electrons in successive levels. You have to start putting them on top because you cannot put them all on the bottom side. So this is the reason why you have this spread in energy here. And the spread in energy here is what each one of the energy levels in the isolated atoms transform into a band. So we have energy bands. A band of energy means a region of energy levels where the energy is continuous. Okay, you can have any continuous level here. Before, when you were actually at at infinite separation, you only have as discrete energy levels here, discrete energy levels. And then when you bring the thing together, bring the distance together between the atoms to form the crystal, you get to the equilibrium separation, and you have these bands of energy that you are forming. So this is what we are going to talk about in the next class. So this is it for now. We are going to try to see some devices and in semiconductors and whatnot. And I know this is not easy digestible, okay? So you really have to read for this, okay? And please ask me questions, okay? So this is it for today, guys. And I see you on Thursday, okay?
All right. Take care.
Okay, bye-bye.